Alright, this is fluid pressure. So the pressure of a fluid can be shown in this equation. So the pressure is equal to the specific gravity times z, or that's the same as the density of the fluid times the gravitational constant times z. And this equation is only valid for incompressible fluids. So that's something like water, but not something that's gaseous like carbon dioxide or anything like that. And z is the depth from the liquid surface. So if this was my liquid level, and I had a plate just like this in the water, then I'm going to have a pressure that's going to be distributed along the plate, and it's going to get larger as the depth goes deeper. So you end up with like a triangle distributed load. So if we had a flat plate of constant width, and we're going to say B is the constant width, then we can draw our flat plate under the surface of the water. It has a length of L. The depth of the top of the plate is Z1, and the depth of the bottom of the plate is Z2. So right here you're going to have W1, which is going to be equal to your width times your pressure. And that pressure 1 is going to be determined from the depth Z1. And then over here you're going to have a higher pressure, higher distributed load, so you've got W2 is equal to B times P2, but that's taken at Z2, so it's going to be larger. Then you've got a linear line connecting the two. So you'd have a distributed load that looks something like this. And then you could take that distributed load to find your resultant force, and that's going to take place at the centroid of this distributed load. And so we can utilize a trapezoid to calculate FR and the centroid. The back cover of your book has a trapezoid, and we'll show you how to calculate the area, which would give you FR, and then additionally where that centroid is going to be located. So our next scenario is a curved plate of constant width. So this is my liquid line, and I have a curved plate underneath the surface. I'm really going to have a few different forces acting on it. So first, this is going to be Z1, this depth, This depth over here is going to be Z2. And so we need to kind of break this up into 3 parts. So up here at this surface, I'm going to just have my W1 equal to B times P1, and that's going to be distributed over this entire surface. I'm going to call this point right here A, this point B, and this point D. So this is going to be equal to the resultant force for AB. Okay? And then down here it's going to vary with the depth, so it's going to start out at the same, at W1 equal to BP1, and then it's going to get larger all the way down to here where it's W2 equal to BP2, and we're going to have that same trapezoid shape. And then its resultant force is going to go through the centroid, call that FR from AD. And then we need to take into account the water that's still here and what weight that puts on the curved plate. So we find the centroid of this area. So this is the centroid of BDA. And it's going to have the weight of the fluid. So basically what you can do is you can find the area of this BDA, then multiply it by your width, and then the specific gravity to find the weight of the fluid that's contained in this area. So overall, your resultant force on this curved plate is going to be F, the resultant force for AD, this one, and then F, the resultant force of AB, and the weight of your fluid. Like I said, the weight of your fluid can be determined by the specific gravity times the width B times the area of BDA. Okay. And then our final scenario is a flat plate of variable width. Actually, I'm going to do this on the next page. Okay, so I'm going to attempt to draw this 3D plate. This is my y-axis, this is my x-axis, and this is my z-axis. And this plane represents where the liquid surface is. So if I have a plate something like this, and it's going to have a distributed load throughout it from the pressure of the water. Okay. And now if we wanted to take just one segment of this, and it would go through the entire plate, not just on the edges, but if I wanted to take just DF. So then I would have DF acting right there. The width of this would be dA. This would be dy, and then I would have x. Alright, so dF would be equal to my pressure times dA, and then my resultant force would be equal to the integral of all of the dFs. So my resultant force is going to go through point P, where P is the centroid of the pressure distribution. So this is also equal to the specific gravity times the integral of Z, our depth, dA. And then this plate has a centroid of C prime. So if the depth to the centroid C prime of the area is Z bar, then the integral of Z dA is equal to Z bar A, such that this can be substituted right there, so that your resultant force is just equal to the specific gravity times Z bar A. And this gives us a good simplification. This is the magnitude of the resultant force acting on any flat plate is equal to the product A of the plate and the pressure, where P is equal to the specific gravity times Z bar, at the depth of the area of the area's centroid centroid C prime. So this is a general rule that can apply to any of the plates, being that the magnitude of the resulting force acting on any flat plate is equal to the product A of the plate and the pressure P, gamma Z, like specific gravity Z bar, at the depth of the area's centroid C prime. Something to note here is that the center of pressure P does not coincide with C prime.